Hello, Pre-Calc Honors students. This is Miss Orloff, and this is 11.3, Day 2, our second day of working with limits. And today our main focus will be on algebraic approaches to finding the limit of a function if it exists. I want to recall that the first thing you should always do is try to substitute in that dependent variable, that input. And if you get an output, if you get a constant, you're done. You found the limit. Woo! But if not, you need to do some algebraic work and then try to substitute again. So for our example today, what we're going to do again is find the limit, if possible, of the given function. And the first one we're dealing with is the limit as x approaches 3 of this given rational function. So if I were to substitute 3 in, I would have an issue right here in the denominator. And therefore, I could not find this limit. However, I have means of algebra, and I cannot drop off the limit as x approaches 3 until I actually take it. So our goal is to find a function, as I stated before, that graphically to the naked eye it looks identical. There's just one difference. X in the domain in the original does not exist, but we're trying to come up with a function that it does, but they look identical again. So we're going to factor our numerator, and we're going to factor our denominator, because as you know, if we are going to create this new function, we can only eliminate our issue if it has a common factor in the numerator. And so these factors divide to 1, and now I can attempt that substitution. Notice I did not write the limit statement down again, because now that I'm able to substitute, I'm actually finding the limit, and I have found the limit to be negative 1/6. Okay. So I have my next problem. I have the limit, and I'm actually going to take the limit as x approaches, let's do negative 3 of x squared over the quantity x squared plus 9. Step 1 is always to think, can I substitute? And if I can, and get a constant out, found the limit to the function. And so we have 1/2. I want to repeat, what does this mean? This means as x approaches negative 3, the output approaches 1/2. It may or may not equal it. In this case it will, but it doesn't always have to happen. The output approaches 1. I also want to reiterate, the limit from the left must equal the limit from the right for the limit to exist. Again, this is the case here. All right. My next example, the limit as x approaches 3. Obviously, something I keep using is 3 here. Of x cubed minus 3x squared minus x plus 3 all over the quantity x minus 3. If I substitute 3 in, that's an issue. So I've got to factor. I've got to know, can I factor? And I wanted to use this example to bring back some old techniques we've learned. I need to factor that. I could do this 2 ways. Maybe I could factor by grouping. Maybe I can do synthetic division. But you need to find a way to factor it. Now, factor by grouping doesn't always work. In this case, it did. And I could have used synthetic division as well. I haven't finished cleaning that up. So let's go ahead and rewrite this statement. Notice again, this limit statement cannot be dropped until I take it. It also is always followed by a function. So now I see that these divide to 1. I can now substitute in. And there we go. Okay, I feel I've moved pretty quickly through the first 3 examples, so I'm going to slow it down here on this example. I have the limit as h approaches 0 of that function. This is actually something the setup of this limit is something very important for a calculus student. We're not going to get into that at this time. So I look at that. I know I cannot plug 0 in. In fact, what happens here is I get something called the indeterminate. I get 0 divided by 0, which is something that is really nasty that we have to deal with in calculus. The good news, you're not in calculus yet. And so I can simplify that numerator. And so I will go ahead and rewrite that squared term, that squared binomial. Okay. My 36 minus 36, since they're opposites, they are equal to 0. I have a GCF of h in the numerator, so I'm going to factor that out. Those h's divide to 1, and I'm now allowed to do my algebra. And my final answer is 12. Okay, my next one looks pretty ugly. The limit is a approaches -5 of 25 over a minus a all over 5 plus a. So we've got this complex fraction. And there's many different ways that a student might approach cleaning it up, making that pretty. I know I can't plug in -5. I divide by 0. In fact, once again, I'd have that indeterminate, that 0 over 0. So my approach is, I know I have to treat this here. That's a weird bracket, but I'm making it even more weird. I have to treat this as an expression. What that means is I can only really multiply it or divide it by a value of 1. I just have to be very clever about the 1. So what I'm going to do is I don't like this a here. So I'd like to multiply that whole numerator by a. But since I can only divide the entire thing by a value of 1, I must do that to the denominator. So I have a divided by a. So I get the limit as a approaches -5. I distribute of 25 minus a squared. I'm going to leave the denominator in factored form. I don't need to distribute it. I really want to get rid of that 5 plus a, and in order to do so, I need to have this in factored form. I notice my numerator is a difference of squares. So I am going to go ahead and factor. And now I'm happy because this divides to 1. And I can now find that limit. And so I get 10 over -5, which equals -2. All right, I'm giving you a you try. It's a pretty tough one, I'm not going to lie, but I know you guys are capable of thinking through it. So, okay, so I've given you a you try, and it's, as I stated, it's pretty complicated. My hint, before you pause the video, is I'd like to clean this up, and that's the issue. And I also know I can only multiply this expression by 1. So pause the video, go ahead and do this. In case you're struggling, here's my hint. Don't forget to distribute to every term. Again, in case you were stuck, look at my work, then pause the video and try to finish this out. Okay, take a minute, look at my work, and see what you think. If you have any questions, let me know. This is the end of 11.3.